Welcome to a new test and teardown video. This time it's a Philips PM5145 Wide Band Generator. It covers 10 Hz to 12 MHz in 6 frequency bands. And the dial is from 1 to 12 here, obviously. Yeah, okay, now when it says 10 here, that means it goes from 10 to 120 Hertz, the first range. We got 2 different modulation modes, so this will be sine wave and square wave. And that one is obviously sine wave with AM modulation. At least that is what I think they want to tell us with this little graphics right there. Of course, variable amplitude output and a really wide attenuator range. Output is 600 ohms, 50 ohms. We got a meter that tells us where we are, probably with the variable here. And for a reason I do not understand, we can turn on and off the meter. Why is that? Well, I think this one is from the mid-60s. And I believe this is old transistor, modern stuff. Also the shiny aluminium look here. That is also the 1960 version of Philips instruments with the good stable handle, the little foot to fold out here so we can have a real nice angle on the bench. A nice rear view of this instrument. And I think they were a little bit ahead of their time, because look at the 230 volts and a good range of voltage variation. And they got voltage in and out, so you can stack instruments without using too many wall outlets. And a nice modern connector, of course. Here is the type number. So it's the 01 version. I think it's really nice to know it's using about 30 VA. Really? Serial number 799. Let's look inside and see what is the state of this instrument. So I've removed all the side and top and bottom. I removed everything so I can see what is going on from all angles. And the only thing I see so far is just a lot of dust. Not a lot of dirt or anything like that, but it's just a thin layer of quite dark dust on all the components, as you can see here. So I want to try and take up all the different circuit boards and inspect if I can find any leaked capacitors. It's not looking really bad from the quick angles we got up here. But it's really neatly designed. There's a funny big capacitor hanging down there. What the? Yeah, that's funny. And everything is in sockets, so we can easily pull it up like that. Maybe there's a little code plug or something, so we can't stick in the boards wrong. There is a little bulb here missing, so somebody stole that. So I need to measure the voltage here and see if I can plug in a new little bulb. I kind of like that, to have this up and running. And there's one little detail I want to show. Look at the mains transformer, how big it is, and the distance to the circuit boards. And I believe the boards here, that has to be the power supply. It looks like we got rectifiers and transistors and stuff like that closest to the transformer, and then it goes more and more oscillator over here, furthest apart from the transformer, obviously. But there's one little thing I want to show that I think is real funny. Look at the different adjustments. See here, this is the oscillator range switch. And around that switch we got a nice shield, but every little range got a trimmer capacitor sticking out of it so you can fine tune it. How cool is that? And the rear panel here with all the wires, I mean, all this is also mains in and out. Those two connectors here, fuse, transistors for the power supplies, voltage selection, everything is just, tied up together so it will magnetically couple together as good as possible instead of making it in two little bunches of cables. So we have all the DC stuff away from all the AC stuff. That is how I would have recommended to do this. And there you have it. The AC outputs goes, of course, to the first module. And see, mains on and off also goes to the switch and all that kind of stuff up there all together. Yeah, that's probably ground here in the middle, a thick, really thick. I mean, really, what the heck? It's 3 millimeters thick. Talk about a ground. Oh, that is something. Why is it so thick? Is that really necessary? And this is the output attenuator in all those decks. What is that? 1, 2, 3, 4, 5, 6, 7 decks with resistors like that to make it so nice. That is a little bit impressive. Here is module H, as they call it. I call it the power supply. It's two completely individual power supplies, and then they're just connected in series. I added some little markings here. This little mark here is the center point. That will be 0. So this is -20, and this should be +20. So it should be easy for me to monitor and check everything is fine. Funny with this layout, really thin tracks. But of course it's not using a lot of power or anything. Here is the schematic of the power supply. I just wanted to show the schematic. It's really nice and simply done with all the transistors and all that things. But what is important here is to note the little dual 2-in-1 transistor for the differential. This compare with the Zener reference and the output voltage. And then if you look at the bottom right, you see a transistor that is connected over a 1 ohm resistor. And this is of course the overcurrent protection. You can probably see when this transistor gets activated, it pulls down the drive signal to the driver transistor that handles the output regulator transistor that is mounted on the back. So it's a constant current or constant overcurrent regulator, not a foldback system, but anyways, it's still preventing all sorts of smoke and overload. So that is quite nice. Here is module F. This is the meter driver and the amp 0 DC. This is this op amp here. It's measuring the output feedback. Here is the schematic for the meter driver and the 0 offset amplifier for the output amplifier. There is a few things I really need to show in this schematic. It's just so fantastic. If you let's look at the meter amplifier, the bottom part of the circuit, okay? So note how balanced and how symmetric this design is made over the plus minus 20 volt supplies. That is just amazing. And of course, they have a transistor at the bottom left where you have a trimmer where you can offset or you can handle the biasing voltage over the two base inputs for the push-pull transistors. And this is not just to handle a crossover and all that. No, it is because there's the two diodes after those two transistors. Those are the rectifiers to make this AC signal into a DC signal that drives the meter. So of course you can adjust the bias and therefore also forward bias the two rectifier diodes to get a much more linear response. This rectifier, I find it really amazing the way that they have done all this. And then there's a little trimmer in series with one of these resistors, and this makes the entire circuit completely symmetric again. And then this meter on off switch, it actually short circuit the meter when it is in off position. But that is obvious why they've done it like that, and that is because all those capacitors that filters the voltage driving the meter. You can imagine if you had this switch in series with your meter, every time you enable the meter, it will just hammer all the way to the right, and then it will go down to the correct readout. You don't want that. You want it to go from 0 and nice and fine up to the correct readout. I don't have a lot to say about the top amplifier. It's just a full feedback with a capacitor. That means you will have 0 voltage DC out in average, and that is exactly what you're trying to achieve of your output amplifier. Here is module E, output amplifier. We got a lot of big, hefty output transistors. That is more or less, yeah, all we got here. Isn't it a little bit funny, the way that this is all done? This goes to 12 megahertz with a design like this. Here is the schematic for Unit E, the output amplifier. I really like this amplifier. It's so clean and simple designed, and the amplifier itself is actually a very good candidate for a copy if you need a good, powerful, super linear driver for your signal generator or anything where you need a lot of voltage. Because at the moment they're running this at plus minus 20, but you could definitely give this, you could copy this and give it a lot more voltage. There's a lot of gain from the input to the output. And if you remove the DC servo, there is a DC servo, and that's the wires that goes down to the previous module. Then this amplifier will work from DC and all the way up to 12 megahertz in this configuration. You also see the diodes in the middle, some normal diodes and Zener diode. That is, of course, the bias of the output stage. We got the two emitter resistors for a local DC current feedback. And then we have two resistors in the feedback system. That is a little bit funny. They're doing it this way instead of measuring the actual output center point. I don't understand exactly why they're doing this, but there's probably a good explanation for that. And that is, of course, the global AC feedback point to the first differential amplifier system. Here is module D. This is only active in square wave mode. Another little dual. Here is the schematic of Unit D, the square wave generator, or well, you can you can call it what you want. But the fun thing is, if you look to the upper left, you see this mode switch, and the upper left is of course the input. And you can see if you are in sine wave, then the sine wave signal from the oscillator part just go straight through those this mode switch, right? So that means, of course, we have the input at the left and we have the output on the right side of this module. So here's the fun thing. This module is just the most complicated way to make a sine wave into a square wave. What the heck? Why are we using that many transistors and differential amplifiers? Two of those using NPN and PNP versions, and a constant current generator, and a feed forward system between the two differential amplifiers and whatnot. And then at the end, there you have it, a diode to an output driver. But I mean, why is it that crazy? Okay, I do understand it works from 10 hertz to 12 megahertz, but I bet any of us could make it half of those transistors. Oh, that is so funny. Here is module C. I call it the Amplitude modulator. We got two transistors in here, coupled together for good thermal stability. Here is the schematic for unit C. This is the Amplitude modulator. And again, let's start with the mode switch at the bottom left. We can now see if this is in the center position. Now our sine wave signal goes up and into this unit C. So input is in the upper left and output is in the middle right of this schematic of the module, right? In the lower left of this module, this is where we have the modulation input. So modulation, the modulated input signal is affecting the amplitude level of whatever comes in and out here. And again, this one handles from 10 hertz to 12 megahertz. I'm totally aware of that. But look how many transistors are they using here. And we have 1, 2, 3 constant current generators. And we have 1, 2, 3, 4 differential amplifier sets that handles the different things that is going on here. It is, of course, a very demanding and very difficult analog system they're solving here. So I'm not laughing at it or anything like that, but it is, today you would just take a little op amp, or you will take a little variable gain stage. And I mean, you should also think about this as designed in the mid-60s and manufactured in the end of the 60s. So this is probably how you do it. But I just love it. Real transistor galore here. Here is module A, the oscillator, and the amplifiers for the oscillator. That will be the 27 mega ohm resistor. Yeah, somebody repaired the amplifier at some point. Here's the schematic of unit A and unit B connected together, and this is to show the oscillator, how it is connected with all the different capacitors and resistors and all the trimmer capacitors that fine adjust all the different ranges. And you can probably see how everything is affecting everything in one big go in this B unit. Let's zoom in a lot on unit A, the oscillator board. I've tried to add a little bit of text here so it's easier to figure out what is in and what is out. So in the bottom left, that will be our input from the capacitor system. Of course, the first pin is just ground to the capacitors. So that is, of course, our super high impedance point. There's a 27 mega ohm resistor, and it says here the other resistor that is in series with that one is between 600 kilo and 4.7 mega. In my unit, they put in a 1 mega ohm resistor, and then there is a DC point set trimmer, and that is, of course, to set the bias of the gate correctly for this field effect transistor. We have a synchronization input, so you can come with whatever kind of signal, and this overrides the oscillator more or less completely. It just overdrives directly in the middle of the oscillator. I bet you can just stop it from oscillating and just sync to whatever you want, right? Then in the upper right, you see something that looks a little bit like an op amp. The idea with this one is a DC servo in all the fast ranges, but is also used as an oscillator in the 3 slowest frequency ranges. You see the 3 capacitors that's marked with stars. Those 3 capacitors goes, of course, to the capacitor and resistor system for the 10 slowest ranges, and they are disconnected in the 3 fastest ranges. And in those ranges, this system is, of course, a DC servo. It goes to the other field effect transistor where you set the DC point of this the oscillator. Of course, I had to remove the cover so we can enjoy this beautiful view of the variable capacitor. And it's made of brass. So beautiful, and it's really big. I think there's something with this anti-backlash gear here, because it feels a little bit, you can probably hear this. It's not supposed to say click clack. There's a little odd feeling to it. I think I'll try and put in a little bit of my Contact 61 spray into that bearing down there, because I think this is where it feels real weird. When I turn here, I skip this gearbox here, and this is made with little ball bearings. In here is this little gearbox. It's in several sections and all that, and even they really tried to make this capacitor really, really big. Probably like a whole nanofarad or something like that, right? But still, you can imagine this one goes to 10 hertz. And I think this explains this 27 mega ohm resistor in the oscillator circuit. Oh, that was just amazing. Of course, I tried adding a tiny little drop to the bearing in here and in there, and both sides, and that didn't help anything at all. But then I added a tiny little spray blob to this part here, and this is where it moves in the outer part, and now it just goes super nice and smooth. So next time you see those gearboxes here, now you know where to spray it up here, and then it goes into this part here now. Lovely, lovely. And now I can assemble this again. That is fantastic. So this will be my first power up. Let's try and connect mains, and it's not using any power. It's using 29 watts. And what do you know? I got a sine wave output here. Let's see what happens. I was actually expecting like bad connections and stuff, but this runs smooth. Oi, 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 oi. Ah, meter on. Even the meter amplifier here is working. Okay, let's try and see if this is going anywhere. Right, so I'm using the 50 ohm output, so I need to select probe 1 to 1 and a 50 ohm load. So I got now 1 volt per division. And is this RMS or what is it? Oh yes, it is. It says RMS. Okay, hang on. That was a little bit weird because look at this. It says here on this plate here, it says open circuit voltage. So that means you cannot load the output with 50 ohm. The output impedance may be 50 ohm, but if you load it with 50 ohm, your output's gonna drop. I mean, look at that. So here's my output. I'm back to 1 mega ohm impedance. Of course that is. Why is it like that? This is weird. But anyway, I got 2.1 volt RMS, and it says about 2 here on this meter. So I mean, it's probably working. What if I put it to 3? And yeah, okay, it says over 3 here. So it's probably okay. So let's put it back to 2 volt RMS, right? Or 2 volt RMS not loaded. Okay, and then I crank on my 50 ohm load, pling, and it goes to 1, exactly half. So now we got the point. Of course, there's an output impedance of 50, and I load it with 50, so we have half of it. All that is perfectly fine. So here's my, let's turn this off again. So there's another cool thing. It says output here is in peak mode, but I think there's a little sine wave here, and this is the square wave. So in square wave, you need to use this scale, the voltage peak scale, for a square wave. Let's see if square wave works. That is some. It's going to stabilize, obviously. Okay, well, we got square wave, and what have we got here? We got, we have 1 volt per division, so that is 6 volts peak. Okay, and it says 6 volts peak on the meter. All right, so this thing here can give a lot of voltage. Let's go back to voltage at 2 volts per division, and we can just hammer it all the way up. So this is what, 15 volts peak, and a lot more. Okay. Not a lot more, but a little bit more. Wow. And then all this attenuation stuff probably also works. Yeah, but I want to play with the modulation, sine wave amplitude modulation. So we're still here in 1 kilohertz sine wave. Then what can we do? What is the frequency range for modulation and all that? And yeah, it's 960 hertz, and I am very, very close here. Maybe we can try and figure out how to calibrate this thing. That could be pretty cool. And what do you know? It is definitely AM modulation, and of course it works. So I've cranked up the output frequency, and it's very sensitive. So this is a 0.5 volt input on the modulation input. And yeah, what else did I want to show? I wanted to show the frequency accuracy of the different ranges, because I really still have this exactly at 10, as accurate as I could set it, right? But look at the frequency readout right there. So this is almost 100 kilohertz, almost 1 megahertz, and the last one should be 10 megahertz. Look how accurate it is. And if I go down, so that was 100k. Again, it's super accurate. This is 10 kilohertz. The 1 kilohertz is a little bit off, so it's 963, and this is 100 hertz, also a little bit low. So it's only the two lowest ranges that is a little bit off. So I want to play a little bit with how do we calibrate this thing. What happened down here? Is it? Why is this not? I don't understand how to get this lamp. How to get this lamp on? Is it on synchronization or what is this? It should go on when I go here. Maybe this lamp is also broken because this lamp here was missing and I put in a new one. So maybe I should put in a new one here as well. Of course we want all the lamps to work. It looks so nice with lamps. I think I figured this out. All the trimmers for the different frequencies, they're actually added and added, all of them. So that means you need to start with the lowest frequency setting and get everything right with the lowest first. And then you proceed up and up and up. If you do it the other way around, I started with 10, and then it affects everything else when you poke around. So this is how it is. Now I've added a little instruction here. I put my dial for 10 as accurate as I can, and then I work my way up. And of course I want to show the different readouts here. So this is 10 megahertz. This is the 1 megahertz. And let's just continue. So this should be 100 kilohertz. This should be 10 kilohertz. This should be 1 kilohertz. And here is 100 hertz. And of course I should be able to dial down to 1 on the dial. If that is possible, I would... What the? How do I fix that? That is the question. I don't need to fix it because it is... I think it is actually my scope that is pulling a trick on me, really. I need much more because then it should say 10 here. Anyway, I think it is really... Yeah, you see? And I think it is really good the way it is now. Super accurate as well. Why not have it as accurate as you can? This is why I love this kind of old stuff. And it's so beautiful. I think I really want to end the video right now while I'm super happy and excited. So thank you very much for watching. Hope to see you soon again. Bye bye.